Okay, hello guys. I'll just want to complete the numerical part related to the last video. It was about measurement methods of airspeeds. One was with a pitot static tube, another was by airspeed indicator. And with the help of a numerical related to the airspeed indicator, we're going to solve out how we can actually apply that one. But just to keep in mind, we'll just do it without any aircraft specifications or the parameters to be discussed. We're just going to calculate the airspeed, which is the true airspeed, with the help of the indicated airspeed and IAS, and also with the help of the Bernoulli's equation, and with the help of the pressure differences between P naught and P. We're just going to calculate the true speed, TAS, true airspeed, with the help of IAS and EAS, which is the indicated airspeed and equivalent airspeed. So without any specified aircraft details or the parameters, or without using the more general form of international atmosphere standards related to the density, related to the air and pressure, that may help to calculate the attitude as well. But right now we're just going to calculate, as I said, the true airspeed with the help of IAS and EAS. So let's see what the numerical is all about and how we're going to deal with it. The airspeed indicator fitted to a particular airplane has no instrument errors and is calibrated assuming incompressible flow in standard conditions. So standard conditions normally of the international atmospheric standards, so we're going to apply the standard conditions of that while flying at sea level. In the ISA, the indicated airspeed is 950 km per hour. What is true airspeed? We're going to calculate the meter per second, converting it from kilometer per hour. 950 km per hour when converting it to meter per second would be 264. Calculation can be done. Obviously you have to just calculate 1000 into 130, 3600. So pressure difference can be this one, which is P naught minus P into a difference of P into half P naught into VE square, which is standard value of density. So standard value of density normally by the is I 1.226 kilogram per meter cube. So that value would be used in this one, which is the half rho naught VE square. So just putting out the value, we calculate the difference. We have this one, which is in pressure, where we calculate the pressure 42670, which Newton per meter square. That is our pressure. Okay, so difference of the pressure. So now P naught over P, we have calculated the assumption of the incompressibility assumption, and we use this and we found out this equation, which was normally used, which was using the Mach number and the relationship of the Mach number, and also the relationship of the coefficient or stagnation coefficient, stagnation pressure coefficient. We use that variation or relationship, and we came across with that equation, which can be solved out for for if you are interested, we can solve it. But this equation is which was due to the incompressibility assumption, and the standard conditions, obviously P pressure is 101,325 Newton per meter square. That is in standard conditions. We are using this numerical in assumption of standard conditions, national standard atmosphere standards. So that is how we're going to calculate it. Putting out the values and solving it out, P naught and this one will going to have adding 1. Okay, that would be this one. And when we're going to have 1 plus they're just using this one, we're going to calculate the 1.421. okay, and removing the also just putting the square and also dividing it by 1 by 7. Okay, so that is how you normally going to calculate. It is 7 by 2 and actual, but obviously when we are calculating in terms of this, it will be round over and will be converted into 2 by 7. So because this value P0 will be converted and this will be reversed, so that will be 2 by 7 and the value we came across it 1.106. Just solving out for the Mach number, we got this, and we know that the speed of sound is A is equal to R of T, that is with the relationship in the standard form. So R in the standard condition it is R is 20.005 with underscore T in meter square per meter per second. That would be the speed. So R is in standard conditions would be 288 joule per kilogram into Kelvin, and that would be the value of R. And solving it out for this equation, 20.05 and R is 288 and into 1 by 2, that we're going to have, because in here it would be the temperature would be 1 and we're going to have this value as 1 as well. So this whole value would be 288 into 1 by 2 obviously as a square root, and then we get 340.3 meter per second. That would be the value. So that is 340.3 meter per second. That is the value calculated. So this is how you're going to calculate, and 340.3 is the value Mach number, and also we have calculated. So we have mentioned that converting into 320 speed corresponding to pressure difference applied to instrument based on static calibration. Okay, that is normally the speed, okay, corresponding to the pressure. So this is how we have calculated the speed of sound. Okay, and with the true A speed is normally this relationship, which is in terms of Mach of alpha 0.728. 0.728 is this. We're just going to calculate the speed of sound of an aircraft. Speed of true A speed would be the Mach number relationship and also the speed of sound at standard condition. Okay, so that will help us to get the relative relationship between the speed of sound and also the Mach number, which is related to the aircraft. So that would be the true airspeed of aircraft. That would help us to get the true airspeed of aircraft with the help of the Mach number of aircraft and also the speed of sound at standard conditions. Just putting it the values and just multiplying it, we get this one. And when it is 3, that is meter per second, converting into that again into kilometer per hour, because our question was in kilometer per hour. So this would be 891. The difference from 950 would be just 59. So in this case, obviously rho density is equal to 1. If neglect compressibility, calibration will lead the airspeed indicator to overestimate the true airspeed by 59 km per hour. So because density is 1, we have neglected compressibility, and the airspeed calibration will give us or the overestimate the true airspeed by 59 km per hour, which was actually given in the question. So that means that was without any compressibility in the standard condition. I hope so. Okay, the indicated airspeed is this one at sea level. Okay, that was in the sea level while flying at the sea level in the IS, in the International Standard of Atmosphere. I believe the indicated airspeed is this one. So this the airspeed was given at this level. We have to use the standard conditions and we have to use the assumption that there is no compressibility. But obviously the airspeed indicator will just give us then an overestimation, because here what we have used is the Bernoulli's equation, okay, and we have used this Mach number, which is the incompressibility assumption. Okay, that means there is some compressibility. There's no incompressibility assumption. We have used it in incompressibility assumption. Because of that reason, there is a difference. We have applied Mach number, and because of Mach number, and that is the equation, we get the difference of 59 from the actual 950. So that would help us to get the true airspeed TAS of the aircraft with the help of EAS, IAS by applying the standard conditions. And obviously there's no parameters of the aircraft given, but in the next example, that would be the lab actually question, and we're going to calculate more specifically the international atmospheric standards and in the standard conditions with the given parameters. We're just going to help draw a paragraph for some and explain further what is the value of those standard conditions as well. So I'm going to end up my video. Hope to see you again. Till then, take care and have a nice day.